I'm just trying to get this going.
And you can start already. Thank you very much.
Okay. So this is quite a broad talk. I wasn't fully aware of the audience. So what I will do is introduce things from scratch, and we'll build up to black holes and the frontier problems. So I'm going to start with a brief history of the question of what is space-time and how we got to our present understanding of space-time, and then we'll build up from there. So there are three important views of space-time that have led to the current development. And the beginning is with some writings of Aristotle, who says that every sensible body is by its nature somewhere, and that's about space. And his second statement is time is the enumeration of continuous movement. And so that's quite broad. It doesn't say much. And many other people before and after Aristotle have said things like this. But what we take away is the basic notion that there are space and time events which will be labeled by a time parameter t and some location x, y, z in three space dimensions. And so space-time we can think of as a set of all possible events. And there's some important basic questions about this. And the basic questions are, um, can you still see my slide?
Yes, we can.
Yes, okay. Something's gone wrong at my end. Can you see the full screen?
Yes,
In the full
Yes,
presentation.
okay.
in the screen, full screen.
Okay. Okay, something has gone wrong at my end. Just sorry about that. Just give me 1 second. I'm not able to move to the next slide. Just something has gone wrong. I'm just going to stop share and reshare. Okay, now it's good. Yes, so the basic questions are, what are the spatial and temporal relationships between these events? And the second basic question is, what is observer dependent and what, if anything, is intrinsic or observer independent? And so essentially, this is the picture we have in mind, that there's time going up and space going to the side. And there's a separation delta t in time, which is the vertical line, and there's a separation between the two events delta s, which is along the horizontal line, and there's a delta L, which looks like the hypotenuse of a triangle. And so Galileo's answer is that delta t is basically the time of the second event minus the time of the first event, and the separation between the events is just Pythagoras' theorem. And the two are separate and disconnected. So space is separate from time. And Einstein's answer to this was different. And his answer is that the separation between space-time events is is given by this formula: c squared separation in time squared minus the separation in space squared, or up to an overall sign. So let's take a step back, say a few more things. So Aristotle stated that there's a state of absolute rest, a single special frame of reference for looking at all events. And this means that all observers, regardless of their state of motion, whether they're moving at relative constant velocity or they're accelerating, all of them agree on the separation delta s and the time separation delta t. And They're given by these formulas, although he didn't write them down in this way. Relative, a constant relative velocity. And given any two events, Galileo, I already wrote this down, all inertial observers agree on delta t, but they can disagree on delta s. So time is absolute, but space is not absolute. But the formulas are quite similar, and the delta s can be transformed to be velocity dependent if there's a relative velocity between observers. And then the third view is Einstein's. There's no such thing as absolute rest. There are infinitely many preferred frames of reference called inertial frames, same as Galileo. And those inertial frames are all observers that move at constant relative velocity. And then the important thing is inertial observers disagree on both delta S and delta T, but they always agree on this new thing. Delta L squared is C squared delta T squared minus delta S squared. And so this new formula says that neither space nor time are absolute, but they're completely linked, and observers will agree only on this combination of these two things. And so you can think of this as a new rule for finding space-time distance between events. And you can think of it as a generalization of Pythagoras' theorem from space to space-time. Not quite a natural generalization because there's a minus sign in there. So what does this imply? I should say one more thing about this, that this has actually been experimentally verified repeatedly. So there's no question that this is the new and correct formula. So now we come to implications of this formula. There are two basic notions which are important to understand: light cones and whirl lines. So the new Pythagoras theorem for space-time is this. We can write it in differential form. ds squared space-time separation squared can be written in this way. And this formula is called the metric. It fixes the paths of light rays, which are also called null curves, by setting delta S squared equals 0. So what's interesting here is you can have, with this formula, a separation such that the distance is 0, but delta t is not 0, and delta x and delta y and delta z are not 0 because of the minus sign. You can have more space than time, or more time than space between events. And so here's some pictures indicating this. The first picture on the left has got a point P, and you can see that associated to each event P is a future and a past light cone. Light cones are special because all observers agree on the light cones. And so in the left picture, P and A are related in a time-like way. B and P are related in a space-like way. The future cone contains all events P, all events that P can influence using light or sub-light speed. And the past cone contains all the history visible to P. So the left picture is in 2 dimensions, the right picture is in 3 dimensions. And you can think of these light cones as throwing a stone in a pond. You see this ripple going out. You take pictures of it and stack the pictures, you get a light cone. And so null curves are the light trajectories. There's one indicated there, the dotted line on the left, which just runs tangent to the light cone, the past light cone and the future light cone. The picture on the right tells you what's a time-like curve, which is sub-light speed. And all the time-like curves are contained within the light cone. And that's what is familiar with all of us. We can only travel on time-like curves, and we cannot approach the speed of light or go faster than the speed of light. So the light cone is a central object in thinking about space-time with Einstein's new formula, or now old 100-year-old formula, more than 100-year-old, 120-year-old formula. And then we have something called a whirl line of an observer moving in space and time. Looks like this. There's a tangent vector, dx dt. And the line, as you can see, the whirl line is always contained inside the light cone at every point. You can think of space-time as just full of light cones. This particular picture, all the light cones all point in the same way. They're like soldiers lined up in exactly the same way because we're thinking of the basic Einstein's formula that I just gave. Okay, so now we come to what is curved space-time and what is Einstein's equation. So the basic formula we had, how do we curve space-time? And so I'm going to give it algebraically rather than pictorially, and then we'll see some pictures. The basic idea is you take the formula for the distance between 2 points, and you put functions of space and time in them. So here's the simplest example. We have this modified formula. And the only difference between this and what I showed you earlier is there's this factor a squared of t sitting there. If a is 1, then it's exactly Einstein's formula, and that corresponds to flat, what's called flat space-time, not curved space-time. But as soon as you put the a in, something strange starts to happen. What this is telling you is that the distance between two space-time events depends on the time and it depends on the time through this function a of t. And this is probably the simplest thing you can write down. Now, what does this mean? So the first observation about this metric is, in fact, this is the metric that describes a large-scale structure of our universe. The only thing that's missing is what exactly is this function a of t and how does it change? So the other thing we learned from this formula is that space is flat because of dx squared plus dy squared plus dz squared multiplied by this function, but it gets uniformly stretched depending on the scale factor a of t. So space-time is curved, but space is flat. And this a of t is determined by the matter in the universe through Einstein's equations, which I haven't told you about yet. This is just an example of what a curved space-time looks like. And you can think of some special forms of a's. So if a is e to the some number times t, then it's called an inflationary universe. And if a goes to 0, something strange happens. If a goes to 0, space-time starts to shrink, and the distance between two space-time events just depends on t, and the space part disappears. This means all of space is squished at a point, and that is called the Big Bang singularity, or at a later stage, the Big Crunch singularity. So I'm going to pause here to see if there are any questions. We talked about just 3 things, the new line element, or the metric, or the formula for the distance between space-time events, and then a generalization to what curved space-time is like. In general, you can throw in any functions of x and t, and what that would mean is that the distance between two close space-time events depends on the location and depends on the time. It changes from place to place, and that's the idea of a curved space-time. Okay, so here's a picture of a particular type of scale factor, and that gives rise to our current understanding. There's all this matter. We're not sure about what types of matter we have. We're not sure about all kinds of details, but this is our current understanding of how things started. The big problem with A going to 0 is at that quantum fluctuations point on the left, which we still don't understand. There are lots of ideas about it, but we don't know what's happening. So this metric underlies this particular picture. Now, what happens to light cones? So light cones are fixed by the metric. All observers agree on light trajectories and cones, which are given by the formula that the distance, space-time distance between events is exactly 0, which means the same amount of time as space is what a light cone is in the formula, so the net result is 0. And curvature of space-time deforms light cones. So if you have functions thrown in, the light cones change direction, they distort, they twist, and so on. So here's an example of a light cone for cosmology. Here I've suppressed dy squared and dz squared. So we just have minus c squared dt squared plus a squared dx squared. We set it to 0, and we get dx dt is equal to plus or minus c over a. Now, if a was 1, we would just get the velocity is c. But a is not 1, a is some function of t. So you can see that the light trajectories are given by this formula, that dx dt is plus or minus c over a. And so whatever a is doing, that determines the light trajectories. And so essentially what we learn is the functions of the metric affect light propagation in this very simple way. It's all really all very simple. If you understand in the beginning, that's the beginning, and then we throw in functions into this line element and proceed from there. Okay, so what's Einstein's equation? So Einstein equation says that there's a left-hand side, and the left-hand side is the geometry of space-time determined by g. What is g? G is the formula for the distance between 2 points. It's got all kinds of functions in it, and we don't know what those functions are. And the right-hand side is whatever matter you want to put in the universe. So the right-hand side could be electricity, magnetism. It could be quarks. It could be fermions. It could be anything on the right-hand side, and you put it on the right-hand side, and Gn is Newton's constant. In general, these are extremely complicated set of equations, and we can't solve them. Even in simple cases that are slightly complicated, they have to be put on a computer to solve. And so very little progress in understanding the full structure of these equations. The unknowns in this equation, as I mentioned, are the space-time metric G and all of the matter variables together, electric fields, magnetic fields, whatever you want to put on the right-hand side. And so it's a remarkable equation. It says that all of space and time and all of the future evolution of matter is determined by this equation. There's no other equation in science quite like this one. Now, there are special classes. People want to solve these equations in special cases. And the special case is what we call the vacuum. Let's pretend there's no matter on the right-hand side. So put 0 on the right-hand side. So you have this formula space-time geometry equals 0. Now, I put space-time geometry is something made out of G. It's not a simple G. It's some complicated version of G put in there. And then you solve for the metric G. It turns out that even when there's no matter, you can get curved space-time coming out. I'll show you an example of that. But in general, there is matter. And the idea is summarized by John Wheeler. It says, matter tells geometry how to curve, and geometry tells matter how to move. And the little picture here gives you an example. There's a sun sitting there. It's curving space-time. There's the Earth sitting below, also curving space-time, although it doesn't appear curved. And then one of the effects that are shown here is how light gets distorted by the curvature of space-time in exactly the way I mentioned earlier. Because when you have curvature, you distort light cones. And so the apparent positions of stars can appear different if the sun is sitting in the front, creating a dimple in space-time, or if it's not creating a dimple in space-time. And so that was the first experiment. This picture gives the first experiment that was ever done to test a solution to Einstein's equations. And it passed that test. That was in 1919. So that's the general idea of Einstein's equations. Now let's turn to black holes. So the first solution to Einstein's equations was found in 1916 by Schwarzschild. And here is the solution that he found. He put 0 on the right-hand side, spherical symmetry, and solved it. This parameter m is an integration constant in the equations. In this case, the equations become kind of simple. You can solve them by hand. One of the very few cases where you can solve the equations by hand. So it's got, you think of this in spherical coordinates. There's a time, there's a radial distance from the center, and then there's the omega squared, which is the metric on a sphere. So just think of spherical coordinates with the origin at r equals 0, the origin where x equals 0, y equals 0, z equals 0. And it's got these two functions in it, 1 minus 2m over r, with the power +1 and 1 minus 2m over r to the power -1. Now, what does this describe? There's some interesting features of this metric. One thing to notice immediately is what happens when r is 2m. When r is 2m, the thing multiplying dt squared goes to 0. The thing multiplying dr squared becomes infinite. So something's going wrong at r equals 2m. And then if you notice there's something else going wrong, if r goes to 0, the thing multiplying dt squared blows up, goes to infinity. And so these two are very strange things which held up understanding of this simplest of Einstein's equation solutions held up understanding it from 1916 all the way to the 1960s when this was finally understood. That's a long time to understand a simple metric, but that's the way it was. And then it was understood that r equals 2m is not a problem, but it's a very strange surface. And it's called the event horizon. And r equals 0 is a problem point. It's where the curvature of space-time becomes infinite. And I've indicated here some light lines. All these curves, the ones going out, the horizontal axis is r, the vertical axis is t. And all these lines going out are light rays going outwards, and all the lines going in are light rays going in. Whenever we think about pictures of space-time, all we want is to plot the light trajectories and put in the light cones. That's the best way to understand. If somebody gives you a metric, this is the first thing you do, is ask, what are the light trajectories, and draw in all the light lines. That may require you to solve a simple differential equation to get all the light lines and draw lots of them with different initial conditions, and this is what you get. Now I'm seeing are there questions in the chat?
I think we
Did we
can.
answer?
I think we
We can
can
proceed?
and take the questions at the end.
Okay. So this is a picture of the light cones that we get from this particular metric. Okay. So as I said, it took several decades to understand this simple metric. And now we're much better at understanding metrics if somebody gives us a metric because we have techniques to understand them. And the first step is always, let's follow the light, draw in all the light curves and see where we end up. Okay, now how do black holes form? Black holes form when matter collapses. So there are two pictures of black hole formation here. And on the left, R is horizontal and T is vertical. And there's the horizon. There's a curvature singularity. The bottom left on the left picture shows the surface of a collapsing star. It's all falling in. The vertical line on the right shows you a distant observer who's watching all this. These right here, all these lines going out are light rays emanating from the star as it falls in and then becomes a black hole. So all the matter disappears. The observer is sitting outside and we get a black hole. On the right is more of a two plus one picture as opposed to 1+1 picture. It shows all kinds of light cones. There's the collapsing matter and shows some light cones as a curvature singularity at the end. And this is ultimately what we think happens to all collapsing matter if it's sufficiently dense. It collapses in towards r equals 0 because of gravitational attraction, which is the same in Newtonian gravity as Einstein gravity, except the nature of the theory is very different. And you can see that in these light cones on the right side, if you're sitting on the event horizon, that's this gray area is inside the event horizon. The boundary is the boundary of the event horizon. If you happen to be near the event horizon, you can send a light ray out because that's the future. Future is upwards. But if you're on the event horizon, you can only, any light ray falls inwards, focused inwards. So the event horizon is tangent to the light cones, as you can see on the right diagram. And so this is what we think happens in classical black hole formation. nicely summarized by Faz. Okay, so we come to detection. Now there are many different ways that black holes have been detected, and the most recent ones have to do with looking at binary black holes and the merger of binary black holes which give out gravitational radiation. So this is a uh, image from the LIGO-Virgo collaboration, and this is not up to date. This is a few years old. Since then, they've detected many more. On the vertical axis are black hole masses, and each of these dots shows um, the two dots merge to give the bigger dot. That's the way they've constructed this picture. And the numbers on the bottom horizontal axis are the names given to these merger events. Each of them has been detected. And now I think there are hundreds of them. This one contains only a few. So for example, if you look at the one on the far right, shows these two green blobs forming this big glob. And that was one of the largest black holes mergers ever seen. So the resulting black hole is about 150 solar masses. And the two merging black holes on the right one was around 80 and the other is around 60. And so how do we know all this is happening? So there are calculations done, numerical calculations of the Einstein equations in general relativity. This is all classical general relativity. And what they've done is create lots of templates, calculational templates of what the gravitational wave signal from black hole mergers look like. And when they see a signal, they go through this database of templates to see which fits the closest to what has been observed. And so there are lots observed already. There's no doubt that black holes exist. There are other black hole detections that have been done, and they involve other things. You've seen the images of the Event Horizon Telescope. The oldest indirect detection of gravitational waves was with the binary pulsar system, whose orbit was decaying slowly, and it was watched for many years. That led to a Nobel Prize. And of course, these pictures, the first such detection also led to a Nobel Prize. And so I could have put up the current picture, but it's very cluttered because it's got so many other events on it. This is just ongoing, and it seems like every month they discover another merger of two black holes into a bigger black hole. So this solution that was found in 1916 um, has been verified. Einstein's equations have been verified repeatedly. But there are problems. So let's now come to the last step, which are the frontiers. And so the frontiers involve what we understand to be the fundamental constants of nature. So in gravity, there's a Newton's constant g, and when you combine it with the speed of light c, that's the domain of general relativity, g and c. And if you want to bring in quantum theory, you have to bring in Planck's constant, and you can also bring in the Boltzmann's constant, which concerns entropy. And we can combine all these to make some interesting quantities. The first is the Planck length. We have the Planck mass. We have the Planck time. And we have the Planck temperature. And so Planck temperature is the only one that involves a Boltzmann constant as well. And you can see the values on the right side, the strange looking values, except perhaps the Planck mass, which is about the weight of a cockroach. And the Planck time is tiny. The Planck temperature is extremely hot. And so what these numbers indicate is that when you bring in h bar, interesting things happen. There's a fundamental length, a fundamental mass, and a fundamental time. And you expect that general relativity must change because of these quantities. If you remove h bar, you can't make any of these constants. They all depend on the square root of h bar. If you look at these quantities, they all depend on the square root of h bar. So h bar is not there. There are no fundamental length, time, or mass. Or you can construct density, you can construct power. Interestingly, if you construct Planck power, which is Planck energy divided by Planck time, the h bar disappears. And that's just a curiosity that there's only one natural quantity, power, which doesn't have an h bar in it. I didn't put it here, but you can just work it out from these things. So what are the implications? So there's few other things that I didn't mention. One of them is that if we have quantum matter, not classical matter, quantum matter plus a black hole, then so when we have quantum matter plus a black hole, Hawking discovered that black holes are not black, they actually radiate and their mass decreases. And that's led to quite a few puzzles. The main puzzle being that there's information loss because you can throw anything into a black hole. You could throw a quantum state into a black hole, the black hole mass increases, and then the black hole radiates and comes back to a black hole of the same size plus radiation. But the radiation is in a mixed quantum state, and the initial state you threw in was a pure state. So there's something strange going on in the interaction of quantum matter and black holes that we don't understand. The second thing we notice when we introduce H bar is that because the metric itself is a dynamical entity, space-time is subject to quantum fluctuations. What does that mean? That means that light cones and causality become fuzzy. Light cones become subject to quantum fluctuations. How does that work out? This sharp separation between time-like separated events, light-like separated events, and space-like separated events becomes fuzzy. So we lose that information to some extent with quantum gravity. Next question is what happens to the black hole singularity? Black hole singularity is a point where mass has infinite density and space-time curvature is infinite. Whenever we encounter infinities, like we do in quantum field theory, we know there's a problem. So basically, it's an indication that general relativity is breaking down. And breaking down and becoming what? What is to be replaced? What is a quantum theory of gravity? So all these questions lead only in one direction, that there is a breakdown occurring. And one of the questions that comes out of this is, what is the final fate of a black hole? So we understand that matter collapses to form a black hole. And the black hole evolves further. Classically, in classical general relativity, a black hole is a stable object. It's not going to go anywhere. But quantum mechanically, even with quantum matter, the black hole is no longer a stable object. And so something has to give. Now, in terms of a singularity, the only way to avoid a singularity is if we go back here, we can actually calculate a Planck density. All we need to do is take the Planck mass and divide it by the Planck length cubed, mass per unit volume, and you get a Planck density. And the Planck density is a huge number. You can work it out from this. And so something must happen at the Planck density. It should be the maximum density allowed, which is a large number, but it's not infinite. So the question is, what happens to a black hole? Does it just become a giant lump of matter at the Planck density, or does matter go in and bounce back out? We don't know, but there are many ideas floating around. And I'll just mention one of those, and this is some work that I've done with collaborators here. And the new possibility is that we looked at a simple model, and in this model, we looked at matter as just dust, and a calculation showed that it's a numerical calculation, shows that black holes end in a shock wave, and the black hole ultimately completely disappears. And so this is something I'm still thinking about, and we want to generalize this work from dust to other types of matter. And all of this is in spherical symmetry, because outside of spherical symmetry, it's very difficult to do any calculations outside spherical symmetry. We don't even understand the spherically symmetric side of it. And so I will end there so we can have a good discussion and open it up to questions.
Gee, thank you very much, Viqar Sahab. So wonderful. It was indeed a mesmerizing lecture that we have heard. Now, I guess we are open to take a couple of questions from the audience if they have.
Oh,
I have seen a
my one quick question
yes, sir,
is,
please.
can you just send us the reference to this paper that you showed at the end?
Yes, I can do that. I'll put it in the chat.
Actually, send it to me directly as the
Okay.
paper. That would be great, whichever way.
Great.
Viqar sir, there are some questions in the in the chat room. So could you please go through these
Okay.
questions and answer some of them?
I'll go through them. So we can ask a question. Any questions? Okay. The first question is dimension of the scale factor. It's dimensionless. Somebody answered that already. The reason it's dimensionless is that the distance between space-time events has a distance of length. It's c times dt or dx. And so length squared is dx squared and dy squared and dz squared. So a squared is dimensionless. A is dimensionless. The next question is, why does space-time specific always... Next question, no, there's no downwards or upwards in why space-time curves like a fabric. It's only an analogy. And it's very hard to draw any pictures. This is why I think we should think about this in terms of what happens to light cones. The stretch fabric analogy is the closest that one can use. There's no downwards or upwards. It's more abstract than that. If light always travels in a straight line, how could it bend in space? Okay. So how does light travel? How light travels is not a straight line. How light travels is determined by the metric of space-time, because the metric of space-time is given by the formula that for flat space-time is given by the formula that Einstein gave. In that case, it looks like a straight line, but if there are functions of space and time in the metric, then it'll look curved to you, but it's still light propagation. So just like when you throw a ball into the air, you can throw it straight up and it comes straight down. That looks like a straight line. When you throw it at with some different initial conditions, it's a curve. And so you have to solve equations to find the trajectory of light. It's the same here. You have to solve equations to find the trajectory of light. And the answer is what you get by solving the equation with those initial conditions. So next question. I see people are already answering questions. So should I answer all of them? What does quantum matter in your last slide mean? If light has no mass, so how can it bend due to gravity? Well, light is following the solution to an equation, which is a geodesic equation, the shortest distance between 2 points. It's not necessarily a straight line. What does quantum matter mean? It means that it means that you solve the Schrodinger equation to find a state. That's what quantum matter is. Classical matter is Newtonian mechanics. Quantum matter is the Schrodinger equation. That's how matter in quantum theory is described by a wave function. So stretch fabric analogy, we've done that. What happens at event horizon is a space-time or a firewall. Will we ever be sure about it? Well, it's definitely not a firewall, I can tell you that. That was just an argument, and there are many criticisms of this argument. You will not get destroyed if you, or get burnt alive if you walk into the vicinity of a black hole horizon. It's a normal point as far as general relativity is concerned. Why does light have a definite speed in space? It's not that light has a definite speed, it's that the structure of light cones is fixed. And c appears in the metric of space-time. C appears in the formula for the distance between 2 points. And I think the important thing to understand about light propagation is that you have to solve an equation to find the trajectory of light once you know the metric. It's no different from solving the equation for throwing a ball in the air. It's the same thing. And so we have to move away from thinking about light following straight lines or curves or whatever. Light is a very special thing that's given by the distance between two space-time events being zero, and you have to solve that to figure out what light is doing. And so ultimately, the primary object is a space-time metric. And what we want to understand is what matter gives rise to what space-time metric. Once we have that space-time metric, then we work with it. It's telling us what it's telling us. I did mention already that the world's simplest and first solution to Einstein's equations took about 60 years to understand. And so maybe because enough people weren't looking, people were looking away trying to do quantum field theory, and nobody was paying attention to general relativity. And had they been, I mean, two revolutions happened at the same time, quantum theory and general relativity. And so it was a matter of how much attention are you going to pay to one theory versus the other. So when people started paying attention, we started understanding. Can we get experimental evidence of the quantum nature of gravity in the near future? Good question. I'm sure you'll hear about it in the papers when that happens. So I don't see it happening anytime soon in the next decade. Next question is AFT 0. There's a singularity. Okay, so all I was saying was I was trying to explain what functions in the metric can do to the metric. And I wasn't talking about the beginning of time or the end of time or anything. If you have a function like a of t in the metric, the way I wrote it, then all one can take away from that is different values of a stretch or contract space. And so a equals 0 means that you're multiplying dx squared plus dy squared plus dz squared by 0, which means the spatial distances have shrunk completely to 0. That's all I was saying there. And there's a entire separate question of what time really is. That's another talk or more than one talk about how we think about time in general relativity, how we look at this t that appears in the metric and compare it with the clocks on our tables. That's another problem that we don't fully understand because clocks are made of matter. If clocks are made of matter, they go on the right-hand side of Einstein's equations. Okay, so how do we deal with that? So there are many questions that are not understood. For practical purposes, for experiments, we have an idea what this t is, for example, for the bending of light in the vicinity of the sun. The t we're using is, well, we're not really using t, we're locating positions of stars and seeing what the relative position difference is. Can we predict any observable effects near the singularity of a black hole? Well, we think that singularity shouldn't exist. Singularities, as far as we know, are hidden behind event horizons. And so the physical effect when you get near a singularity is what's called a tidal force whenever gravitational forces are strong, and they would be strong near a singularity. What would happen is your shoulders would get, left shoulder is following a trajectory to the center. Your right shoulder is following a trajectory to the center, where the singularity is. So as you fall, the trajectory of your left shoulder and right shoulder are getting closer and closer together. So you're going to get squished like a pencil. That's what will happen to you if you get near a singularity. How much matter can a black hole consume? Is there any limit? No, there's no limit. It can keep consuming. In fact, the entire universe may end up in a gigantic black hole at some point. LQG gives a bouncing fluid. Please explain a little, what does that mean? Okay. So if you look at the Einstein equations and you put in some sort of quantum gravity correction, the one way to think about this is that there's a maximum density that can be achieved, which is something like the Planck density. So the universe will shrink, shrink, shrink until it reaches the Planck density. And then once it reaches the Planck density, it stops because you can't squash matter more than the Planck density. And then what happens? Then what happens is that there's a bounce. If you compress something, it bounces back out. That's kind of a very crude way to put it. But the equations say that there's a maximum density with a scale factor in the universe that A, as a function of time we're talking about, reaches a smallest value. It doesn't reach zero, it reaches a smallest value. And then the equations predict that it changes sign, the rate of change changes sign, and A starts getting large again. So that's roughly what is going on. The input is that there's a maximum density, which is the Planck density, beyond which matter cannot be compressed. So what happens to time in black holes? Well, in general, the issue with what clocks do, you can look at that Schwarzschild metric, which is the simplest metric. There are numerous physical phenomena associated with that metric. One of the phenomena associated with that metric is that the closer you are to the singularity, the slower clocks would run. And the farther away you are, so in other words, if you get very close to the singularity, clocks will stop. It's just a calculation. I don't know how to explain it beyond that, but there are many other effects associated with this too. One of them is that if you look at the Earth or you look at some heavy star and you have a light ray emanating from it, it's not a black hole, so a light ray can escape. Then what happens is that as the light ray escapes, its frequency shifts more to the red, and so it's called the gravitational redshift. Conversely, if something is falling in from infinity, then its frequency changes. So propagation of light, although still on a light trajectory, its frequency changes as it goes through per space-time, goes through a gravitational field. Is your approach background independent and you worry about sum over topologies? Okay. So ideally, we want to have a quantum theory that is background independent. What does background independent mean? So we have to take a step back and ask what that means. What it means is when we normally do quantum theory, even quantum mechanics of a particle, there are some inputs into writing down the Schrödinger equation. And one of the inputs is the metric. Now, in non-relativistic quantum mechanics, the metric is fixed. It's fixed to be the Euclidean metric, the Pythagoras theorem. When we go to special relativity and do quantum theory, the metric is the first Einstein metric, Minkowski metric. So quantum theory takes input a metric, and that metric is fixed, doesn't change. But general relativity says that there's no such thing as a fixed metric. The metric is a dynamical object. And so how do we do a quantum theory without a fixed structure like a metric? And so that approach is called trying to become background independent. People are still struggling with how to get a background independent theory. And do I worry about sum over topologies? No, it's too far away to worry right now. I can't even deal with background independence, never mind sum over topologies. So it's too far away. Causal set theory, no, I don't think so. Causal set theory is in a very elementary stage. I don't think it can say much about black holes. We don't see charge solutions in LQG. I'm not sure what that means.
In fact, causal sets were not developed for black holes. It was for building up space-time as the universe as a whole. Can't give it for black holes.
So one of the things people do is causal sets are ordered space-time points, and you can construct a causal set corresponding to any metric, but you have to take a metric and then they do a process called sprinkling points on the metric to get a set of points, and then that causal set represents an approximation to the metric. So you're not solving an equation to get it, you are trying to imagine some aspects of a black hole as a set of causally linked points. Why is it so hard to quantize gravity? So it's hard to quantize gravity because quantum theory and general relativity rest on very different foundations. I mentioned this a little earlier, but this is relevant to the question. Quantization requires that, as we understand it, quantization requires that you have a fixed space-time metric that is not bouncing around on you. It's like saying that you're watching a play on a stage. There are people talking on the stage, and the stage is fixed. The stage is not moving. And so if the stage starts to move as the people move on the stage, then we don't know how to apply quantum theory in that kind of situation. So that's why it's so hard. This is the central question, why it's so hard. Because we don't have the crutches that were used to construct quantum theory in the first place.
I guess
Wow, you won. Questions have run out.
yes. I guess we have to put somehow a limit to the questions. But I see there are no more questions coming up. They have reached the saturation level, I guess.
So can I just have one very quick comment, if that's okay, Wajid?
Sure, please.
Well, first of all, it's wonderful to hear your lovely voice yet another time. It's always a pleasure to listen to your talks. And I don't know if Moise is sitting here or not, but if he isn't, I will tell him that you use the correct metric.
I use the correct metric for what?
Oh, he insists that the metric must always be written as delta x squared minus delta t squared.
Oh, yeah, I wanted to change it all back. I think I went back and forth. So, yeah.
So I'll just tell him that you got it right.
Okay.
Thank you.
Oh, thanks for the nice comments.
Thank you, Rizwan. Thank you very much. Thank you, Asghar Qadir Saab, and thank you, Viqar Husain Saab, for being with us. I'm sure there must have been many questions which one can ask after listening to the beautiful presentation that you have given to us. But on behalf of the Pakistan Physical Society, the High Energy Physics sector, we would like to say thank you very much. And we would like to hear once again, anytime, whenever you have the time to talk to our students, to talk to us. So we are very grateful to you, and we hope to see you anytime soon physically in Pakistan among us and amongst our students. So thank you very much, Viqar Sab. And if there are any comments from anyone, please, Jamil or Asar Qadir Sab, you are free. Otherwise, we can close the meeting and say goodbye.
So Viqar Sahab, it's lovely to see you after a long, long time, and hope to see you in near future. And thank you very much for accepting the invitation on such a short notice. And it was really a wonderful talk, and we hope to see you very soon in Pakistan once again. Thank you very
Thank
much.
you. Thank you, Jamil.
Thanks to you, everyone, for being with us. And we say goodbye. Take care.